Illuminated by IEEE Photonics is a podcast series that shines light on the hot topics in photonics and the subject matter experts advancing technology forward.
Hi, everyone, and welcome to today's episode of Illuminated. I am Akhil, and as the Associate Vice President of the Young Professionals and the Chair of the Young Professional Advisory Committee, it's my pleasure to be your host today. I'm a biomedical physicist myself, working at the University of Glasgow as a Leverhulme Early Career Fellow. In my role for the IEEE Photonics Society, I'm supporting and promoting initiatives, very much like this podcast, to raise the profile of valuable young professionals within various sectors. The Young Professionals Initiative is for graduate students, postdoctoral candidates, and early career professionals up to 15 years post their first degree. This affinity group within the IEEE Photonics Society is committed to helping one pursue a career in photonics. We're here to, one, help evaluate your career goals, two, better understand technical pathways and subject matters, refine skills, and finally, grow professional networks through mentorship. Now, on to the more exciting, our podcast for today. Today is a particularly interesting topic that we're talking about. Working in classical and quantum optics myself, and with a keen interest in time-of-flight imaging and sensing, our topic is of a particularly personal interest to me. We're discussing LiDAR systems, technologies, and current questions regarding the state of the field and the future of the field itself. Our very special guest, Professor Pete Dragic, and moderator Rajesh Menon, are here with us. We go into technology, career journeys, advice from within and beyond research. Now, firstly, thank you very much for listening to this episode. I am already certain it's going to be a great one. I will now hand over to Rajesh for the episode and for conversations with Professor Dragic. Rajesh Menon is an engineer and entrepreneur, advancing knowledge at the intersection of optics, nanofabrication, and computation. He is a professor in electrical and computer engineering at the University of Utah, a fellow of Optica, SPIE, and a senior member of our very own IEEE. After receiving his PhD from MIT, he co-founded and led a spin-off company for commercializing maskless lithography. His lab in Utah is exploring a multitude of imaging systems enabled by nanofabrication and computational methods, including miniaturized endomicroscopy for deep brain imaging, ultra-lightweight optics for airborne imagers, computationally enhanced diffractive spectral imagers, and many, many more. Rajesh has also invested in the successful realization of laboratory innovations via entrepreneurship and has spun out 4 companies. It is with great pleasure now that I hand over to Rajesh for the rest of the episode. Take it away.
Great. Thank you very much for the kind introduction, Akhil. And it's an honor to be in this fine company, and very excited to talk about a very pertinent topic, which is LiDAR, which is the topic of this podcast. LiDAR, of course, stands for light detection and ranging. It is a remote sensing technology that uses lasers to measure distances and many more things about the 3D environment, which we will learn about today. Most of us have some familiarity with automotive LiDAR. In automotive LiDAR, laser beam is emitted. It's a pulse laser beam is emitted from a source, and we measure the time it takes for the beam to bounce back off from objects in the environment. This data is then used to create a detailed 3D point cloud of the area being scanned, but including surveying, mapping forests, urban sprawl, archaeology, environmental monitoring, etc. So it's a very exciting technology which is getting very wide usage, which is, of course, the goal of almost any technology that comes out of the lab. Today, we are honored to have an expert in the field of LiDAR, Professor Peter Dragic, with us to geek out about LiDAR. Pete received his PhD from the University of Illinois at Urbana, Champaign in 1999. After a stint doing startups, he returned to his alma mater, where he's currently an associate professor in the Department of Electrical and Computer Engineering. His graduate work focused on the development of fiber laser-based sources for atmospheric LiDARs, namely for the sensing of water vapor. His current research interests range widely from optical materials to lasers and laser systems, including LiDAR. Of particular interest are fiber laser systems, which offer some advantages over their counterparts. However, they also suffer more significantly from power limitations due to nonlinearities. Therefore, much of Pete's attention has also been focused on reducing the impact of these nonlinearities in optical fiber systems for applications such as remote sensing. The first of two current LiDAR projects is an upper thermospheric/exospheric LiDAR for the detection of metastable helium. The other is the sodium LiDAR that will take a ride on a sounding rocket through the lower to middle thermosphere. It is my distinct pleasure to invite Professor Pete Dragic to this conversation. Pete, let us start with an introductory question about, could you share with us how you chose to get into the field of LiDAR and what inspired you to pursue these topics?
Sure thing, Rajesh. Thank you very much for the kind introduction. I'm also very pleased to be here in the company of some really wonderful people, some great minds. To answer your question, I guess this goes back to my undergraduate days. During the end of my junior year, I was looking around for a summer undergraduate research experience, pretty much of any kind. Frankly, I wasn't sure if graduate school was, for me or not. But I was fortunate to find a faculty member working on semiconductor-based, LiDARs, who was also looking for undergraduate researchers. At the time, his group was trying to develop a system to measure atmospheric water vapor concentrations. Water vapor, it turns out, is a very strong and indeed the most abundant greenhouse gas. It helps to trap radiation, keeping thermal energy from escaping the Earth's atmosphere. Some of us understand that to be a source of global warming. Anyway, I spent the summer working on the laser transmitter and became passionate about lasers. And frankly, I've been at it ever since. In fact, I became a graduate student in the same group where I did my undergraduate research. I also had a NASA fellowship during my graduate days from the Goddard Space Flight Center, helping with a similar system actually for the Martian atmosphere. The goal there was to look for terrestrial vents of water vapor that could be indicators of the presence of things like microbial life. What's neat about LiDAR, and this is kind of what keeps me going, is if you like lasers, for every LiDAR that you build, you get to build a new kind of a laser system. And so I think that's really, really neat and very exciting.
Wonderful. Thank you, Pete. It's quite instructive that you were inspired by an undergraduate research experience, which really underscores the importance of supporting and mentoring students, which I think we will come back to later in our conversation. And I'm also fascinated by your PhD work about detecting water vapor in the Martian atmosphere. Clearly, it would be one of the greatest discoveries of human history if we were to detect proof of extraterrestrial life forms, even outside our solar system. This is something I would like to come back to as we go through this conversation. Mm-hmm. But let us begin with something more down to earth. Could you give us an overview of what your group is currently working on? The technologies you're developing and their exciting applications that they will enable.
Sure thing. I'll speak to the two LiDARs that we're developing in our group, both of which are types of LiDARs known as resonance fluorescence LiDARs. So the way that they work is one takes a laser beam, tunes its wavelength to an absorption feature of a species. In the case of our systems, they are helium and sodium. Those end up being actually in the upper atmosphere. Sodium, there's a layer of sodium, roughly 90 to 130 kilometers up. That resides there due to ablation of mainly meteorites as they come into the Earth's atmosphere. And then helium in the upper atmosphere, ranging from about 300 kilometers to about 900 kilometers. There's a layer of helium. Of course, one can imagine if the atmosphere is stratified, the lightest elements will appear at the top. And so what we do there, basically, the principle behind resonance fluorescence is, again, we tune our laser wavelength to an absorption line, like the D2 line of sodium, for instance, at 589 nanometers, that species will absorb that photon and then re-radiate it. It'll re-radiate it as fluorescence, and therefore it goes in all 4 pi steradians, all directions basically. And we're looking from somewhere like the ground or from somewhere where we have a telescope. The helium LiDAR, the goal is to measure out to roughly 900 kilometers, 1,000 kilometers, metastable helium. So what happens there is as solar radiation comes in, and that energetic particles are created, collide with the helium and excite those heliums into an upper state, many electron volts above the ground state. Once you're up there, there's a feature, an absorption feature at roughly 1 microns, 1083 nanometers actually, that can be used to probe the presence of that metastable helium in that part of the atmosphere. And so, of course, we want to make sure our laser wavelength is at 1083 nanometers. What's interesting about this is that's a wavelength that's achievable through fiber laser technologies, among other solid state methods. And what we're interested in doing is creating a high power source that can go up far enough into the atmosphere. Again, it's a resonance fluorescent system, so then that laser signal will be absorbed. It'll be re-radiated to the ground, and we sit on the ground with a very, very large telescope, such as an observatory telescope or something like this, and receive signal back. Again, if we pulse the laser, or we can actually do other techniques to sort of do range resolution, and we can track and we can watch the helium, that metastable helium concentration as a function of time and distance. And that gives us information about the dynamics of the atmosphere. So the helium itself serves as a tracer. It's not necessarily that we care first order about the helium itself, although there are interesting things about that too. It serves as a tracer to give us details about the atmospheric dynamics. That second system is a sodium-based system. Again, at 589 nanometers. That one is not directly producible by a fiber, but again, you start with some sources and you get to a wavelength somewhere in the infrared, and you do frequency doubling, and there's lots of neat ways to achieve that wavelength. But anyway, the idea is there is a layer of sodium, roughly 90 to 130 kilometers, and watching how that sodium moves through the atmosphere gives us information about atmospheric dynamics, the motion of energy from lower parts of the atmosphere to the upper parts of the atmosphere. How do they couple? A lot of that is still not understood by humanity, and understanding the way that functions can give us better insight into creating global energy transport models for our planet. The idea there, of course, the system itself will take a ride on a rocket. What we're looking for in particular for that system is kind of a short range, ranging from the rocket, say a couple to a few kilometers, and we're looking for turbulence effects, mixing effects. So what happens during mixing events, and we're simply using the sodium again as a means to watch that process. It's not so much that we care how much sodium there is. There are reasons why you'd want to know how much sodium there is. For instance, there are guide star applications where understanding the concentration is very important, but we're using that as a tracer to actually watch the motion of the atmosphere.
Wow. So, yeah, it's very, very interesting, and I just want to make sure I understand it. So, in the case of the resonance fluorescence, you are exciting the resonance and watching the fluorescence from the ground. So how is the excitation beam scanned across some field of view, or how does it actually work?
We can scan the beam. Most generally, though, we don't scan the beam. It's kind of line of sight. So we look in one direction. The beam will expand, to some extent. Of course, think about like a milliradian beam going hundreds of kilometers. It'll be a relatively large beam, so we're really integrating across its area. Certainly, we can think about a scan. That becomes a little more difficult as one goes to large scan angles, because the distance to the measurand is a little bit increased in that respect.
Right. And how do you actually get the range information from where the fluorescence came from?
Well, for a LiDAR, you can do this a couple of different ways. The most common approach is to use a pulsed LiDAR, which you alluded to earlier in the discussion today. What you do basically is you send out a pulse of light, and you're basically measuring returns as a function of time. So it's a time of flight thing. So if you get to some point in time where you start measuring information, you could turn that into, or start measuring returns. You could create a distance distribution by scaling via the speed of light, and understanding there's a round trip involved. One of the caveats there, of course, is if you do a pulse system, you want to make sure that your pulse goes out in a way that you don't alias your return signal from the atmosphere. So that means that if you send your pulse out, you want to make sure your pulse goes out and then it leaves sort of the line of sight to make sure that you're not getting returns from different parts of the atmosphere from different pulses.
Ah, yes, I see. That was actually one of my questions, was how would there be potential for ambiguity if sodium at different distances across the layer starts fluorescing from the same pulse?
Yes, it's possible, but because the pulse is propagating at the speed of light through that range, when we receive those returns will be a function of time as well. So if we send out a pulse, yeah. So let's say there are two ranges, x1 and x2. Well, distance equals rate times time via the speed of light, of course. And so when we start receiving signals from the first part from x1, will be a time different from x2, and that's how we can resolve them. But if we have multiple laser pulses that exist at the same time, then it becomes ambiguous to which pulse contributed from which layer.
Yeah. Excellent. Yeah. Very cool. And I would assume that the signal that you receive back is quite weak. Can you comment on that? Like how much, what's the efficiency from the excitation to the received signal, and if that is a challenge, how do you deal with it?
Yes, that is a challenge, actually. You send out a signal that might be, for our helium LiDAR, we're actually envisioning kilowatt lasers. The return is going to be many orders of magnitude below what you put out. Oftentimes it requires photon counting. And so you'll actually have a receiver or a detector, like a photomultiplier tube or an avalanche photodiode or something that's configured to count photons. Of course, that depends on the number of returns. If you have a larger amount of returns, you want to make sure that your photon counter can keep up with the number of photons that are coming back. If your returns are very small or very low, the number of photons, then we have to consider, of course, ultimately scaling the receiver design. So, if our returns are low, a couple of photons such that they're swamped out by the noise that we might get, say thermal noise or background light from some other source, then we think about scaling the telescope. So that's kind of like the trick in LiDAR is power and aperture. So the more power you have, of course, the more returns you're going to get. The more aperture you have, the more of those photons you can collect. You have a larger light bucket. There is, though, a limit to that, especially in terms of the resonance fluorescence LiDARs. The resonance fluorescence LiDARs, actually, I mean, it's almost like a fluorescent material in space. It's kind of like a laser for the most part, kind of up in the atmosphere. And so, if you put out too much of the laser signal, hoping to get returns back, you can actually saturate the layer. And so there's going to be a limitation potentially to how much signal you can get back, regardless of the size of the telescope.
Wow. Yeah. I was just noticing how many different parts of electrical engineering come into play to make the LiDAR work. Everything from optics to signal processing. I'm curious if I were to dig in a little deeper into the laser itself. You mentioned very high kilowatt lasers. Could you talk a little bit about the challenges and complexity of building such lasers?
Oh, certainly. Of course, the laser itself is comprised of many components. There's different ways to achieve laser technology. One, it could be a traditional laser that's based on a resonator, and you kind of achieve high power that way. Other approaches are to create these master oscillator power amplifier type lasers, where you start with a seed laser, perhaps of relatively low power, and then you amplify it. In fact, both of the systems that we're building are based on that technology. The helium LiDAR is nothing more than a semiconductor laser that's amplified by a chain of fiber amplifiers. And then our sodium system is actually a Rayleigh, or sorry, a Raman scattering. It's based on Raman scattering in bulk crystals. In that case, again, it's just amplifiers that are amplifying our signal, and then at the end we double to get the 589 from 1100 to 78 nanometers. To get to the high power, there are several things, of course, we have to think about. One is you have to energize or provide energy to the laser, right? So the pumps, as we call them, have to provide sufficient power, in a wavelength range that the gain material can absorb. That's basic lasers 101. And then you have to consider the modality or the framework by which you're actually generating the light. So for instance, in fiber laser systems, we're after the high power, and for our helium system, we want to make sure that our laser wavelength, not just the wavelength, but the spectrum of that laser lies within the absorption band of the helium. Turns out that in the upper atmosphere, that's on the order of something like a gigahertz. This is all temperature broadened stuff. But anyway, we want to make sure that our laser signal is the spectral bandwidth is much less than the 1 gigahertz. Turns out that in optical fibers, this leads to nonlinearities, in particular stimulated Brillouin scattering, which is an interaction between the light wave and an acoustic wave within the fiber that can greatly limit the amount of power that you get out of it. And so it's not so much that you want to get the power out of it, but you have to then devise an optical fiber then that can also support that kind of power levels while somehow circumventing the effects of Brillouin scattering. There's several ways to do it. It might be beyond the scope of today's discussion. And then on top of that, of course, are all the optics. And so, normally when we send a beam out, if we're going over long distances, it's different if over short distances. But maybe we don't want the divergence to be too large, because as we come up through the atmosphere, we don't want to have our beam expanding to many hundreds of kilometers in the far field. And so what we'll do is to reduce the divergence, we'll do a beam expansion. Of course, all of the the optical components that go into that expansion then have to tolerate that kind of power. So there are a lot of different things that we think about. And then ultimately, as we're running, we think about device longevity. Are there components to that system that might fail over time, especially when you're doing something like a remote measurement, or you're sending a laser system onto an autonomous vehicle, or even a rocket. I wouldn't call that necessarily. It's autonomous, I guess, in a way, but you're just launching it. It's doing its thing. You want the system to succeed and not fail during its flight. And then on top of that too, of course, when you're on a platform such as that one, you think about vibrations, things shaking. What's interesting about that system is it's not so much making the measurement once we get to the layer that we're interested in, the sodium layer. It's the ride that it takes getting up there. And so when things are shaking, it has to survive the ride. Once it gets to the layer, everything's nice and smooth. All the rocket engines shut off, and it's not a big deal. But then we also think about making sure that the wavelength itself is stable enough, again, to be held within the absorption band of interest. If there are temperature fluctuations, vibrations, and things that are happening, there's a possibility of the wavelength walking off. For systems with motion, such as the rocket, now we also have to contend with a Doppler shift. So the fact that our rocket is moving gives us another degree of complexity, in that we have to understand not just the wavelength, but how does the observation change given the fact that the rocket itself is on a moving platform.
Wow, yeah, there's so many layers of complexity that you just went through that I want to peel away a little bit and ask you a little bit more detail. The stimulated Brillouin scatterings is incredibly fascinating phenomena, and I just want to clarify with you. It is where does the acoustic wave arise from in the fiber? So let's start there. I have so many questions about what you just explained.
Oh, sure. I guess the easiest way to think about it, the simplest model is to consider the fiber itself as being at temperature. It's just, it's room temperature, whatever it is. There are vibrations that are present in the material, and so you could think of sort of the glass itself as being a kind of a bath of acoustic waves that are all present. And as the light wave passes through the optical fiber, they'll be Bragg matched with some of those acoustic waves. As your Bragg, the acoustic wave itself, of course, is a longitudinal pressure wave, and if you have pressure in the material, that changes the refractive index, and so the grating itself looks a lot like a fiber Bragg grating. And so your optical wave, when it comes in, will be Bragg matched with some of those acoustic waves. Again, one in principle, but the optical fiber can be an acoustic waveguide, and it can actually interact with multiple acoustic waves and so on and so forth. But to keep it simple, the light wave will scatter from that Bragg matched wave. The light wave will then the scattered light wave will then which is also Doppler shifted, by the way, because the sound wave is moving at the speed of sound. So you have a frequency shift associated with that reflected wave. That scattered wave then will interfere with the original forward going wave. That interference pattern then feeds that original acoustic wave. Because the original acoustic wave becomes amplified, its reflection becomes stronger, and so you can kind of see this positive feedback cycle sort of forming. Eventually, you reach some power threshold known as the threshold power, I guess, where your stimulated process takes over from noise, and you're instead of getting light out of the fiber, much of it gets reflected back towards the sender. So it's a problem that you see not only in lasers but also in telecommunications. In telecom, the easiest way to avoid this problem is to broaden the spectrum. As Brillouin scattering is a coherent process, it requires a line width that's less than the Brillouin line width, which is usually on the order of tens of megahertz. For us, for the LiDAR application, oftentimes we're not allowed to do that because we're trying to make sure that our laser signal lies within the absorption bandwidth of the species we're trying to measure.
I see. Wow, very, very cool. A second topic I was interested in was it's pretty incredible that you're working with these huge powers, and I'm curious if you can comment on how, practically speaking, how these experiments are done in a university lab. Like, I'm sure there are some interesting challenges there.
Well, safety is of utmost concern. So making sure that the students are wear their goggles and all that stuff.
So Pete, the other question I had was relevant to the rocket launching. So can you talk a little bit more about the challenges involved in designing a laser to be launched on a rocket? It sounds incredible.
We have our LiDAR system is comprised of many parts, as we've already talked about. There's the rocket is fairly long and thin, and when it flies, it has to fly in a way that's stable and I guess predictable. But there are multiple components that we have to worry about. So one, there is a telescope that's on board, a curved mirror that's on board the rocket, and so the way it's designed is as the rocket goes up through the atmosphere, different, the fuel pods or whatever will fall off the back end. I'm not an expert in the rocket itself, by the way, but thinking about kind of ruggedization. So one, you have to make sure that telescope or that mirror survives that process. So actually figuring out how to epoxy it to a stable sort of substrate, such that it doesn't crack or shift or move out of place. That's really important. Of course, we have our mirror, and that's in a different place from the laser. The laser itself is on a hardened breadboard. All the components are in machined grooves, kind of where everything sits. Mechanically ruggedized, and of course locked into place with various epoxies. And then the output of that system, of course. I should go back and comment. One of the things about the setup, when one is thinking about making sure that the laser itself stays aligned during that flight is to use components that are a little bit bigger than you would usually use in a lab. It's kind of it's like a typical university laboratory or something like this, teaching lab or research lab or whatnot. So what you want to make sure is, as we have things like lenses and mirrors that direct different parts of the beam to different locations inside the laser itself. If something shifts, like the crystal, for example, the Raman crystal is large enough such that if there's a shift in the position, it doesn't matter because the crystal is large enough to tolerate that change in position. So that's part of a key to that. The other part of it, of course, is making sure that things stay put. You want to make sure that everything is locked into place. We actually, I'm not a mechanical engineering expert, but this is a testament to the kind of multifaceted nature of doing research like this. Is we have people from the mechanical engineering department helping us to design that stuff. It's like I said, very multidisciplinary. It's like how do we? I understand photons and I understand how to generate them, but how then do we ruggedize this thing? Okay, and so that's part of the part of the whole story. And then of course, as our laser is in a different position from the mirror, we'll take for example, our concept is to bring an optical fiber to the output of the laser, and then the optical fiber will bring the beam over to the telescope, and then our beam will kind of couple to the telescope, be reflected from the mirror and outwards in a truly monostatic configuration. And then that same telescope is used for receiving. Another optical fiber on the receiver end, of course, collects that light and then takes that to yet another part of the rocket that has our photodetectors, which are actually photomultiplier tubes. And making sure that stays aligned is also imperative. So it's there's fibers, there's the mirror, there's the laser, and it's the alignment of the various things plus the rigidity, the structural integrity to make sure that things don't break apart, shake apart, or become misaligned. So there's a lot to think about. It's not a trivial task. It's just a lot of things to think about.
That's quite an understatement. It's very exciting, and I assume this is one of the reasons what makes you so passionate about this research, because it's always something new to learn and problems to solve.
Yeah.
I'm curious, once the rocket actually reaches the layer that you're interested in, does it simply float, or do you still control it with motors? How does it actually work?
It's going to basically it's gonna ride up to roughly 130 kilometers, through the fuel that's going to be on board. And once that's spent, the rocket will no longer it won't be propelled. It's going to undergo a controlled fall. And the way that we have it, so the way that we have it set up is it's actually going to be spinning as it's falling. And of course, those are the rocket scientists that figured that out. we don't, again, there's a whole team of people involved in this development. But it's gonna, as it's coming down, it's gonna kind of rotate. And so what we're gonna do is we're gonna get a kind of a 360-degree field of view of the returns or the turbulence field that's in the vicinity of the rocket. Again, this isn't turbulence caused by the rocket. It's in principle turbulence related to atmospheric dynamics. And that fall process is actually quite smooth. Actually, I was
wow.
The way that they describe it is like a turbulence-free kind of floating that happens, and we can only measure through the sodium layer, which ends at about 80 to 85 kilometers or so, and then the rocket itself will land in the ocean. Near the shore, and we'll retrieve it to hopefully it'll survive, of course, that process, the impact, so that we can use it again.
That's incredible. You'll get your laser back.
Well, that's the hope. That's the hope. You never know.
So let me ask you about another challenge that many of the listeners are probably aware of is, since we are in LiDAR, since we are trying to measure such a weak signal, can you talk a little bit about the detection challenges on the detector side?
Certainly. Um, Again, when you're designing a LiDAR system, you kind of have to have a priori sort of a sense of the signal that you expect to get back, and that will help to guide your choice of receiver or detector. To first order, of course, you have a wavelength that you're producing, and then some other wavelength, maybe the same wavelength or a different wavelength, will come back, and you want to make sure that your receiver, of course, spectrally overlaps with what you're trying to detect. So, for instance, if you're trying to look for a 1300 nanometer signal with a silicon detector, that's not going to work so good. So, of course, that's the first a priority. The second is to understand how much power or how many photons you expect to get back. If you're expecting a large signal to come back, oftentimes if you're close range to an object and it's perhaps an automotive LiDAR, you might get a lot of signal back, and so you can use a standard detector for something like this. Whereas if you are expecting to get just a few photons back, then we have to move to a photon counting device. So those could be photomultiplier tubes. Photomultiplier tubes work on the photoelectric effect. Basically, you have this material. A photon comes in. The energy is above the work function. It spits out an electron, and then that's amplified through a chain of what are called dinodes. And you get maybe a factor of 1 million amplification in that case. Just like with anything else, the higher the work function, the lower the noise that you have. Same as with semiconductors. You can also think about photon counting semiconductors. However, the smaller the band gap, the more noisy they become, as thermally generated electrons can traverse the band gap. And so oftentimes, when we're dealing with longer wavelengths, where like the work function's low, or the band gap might be low, then we have to think about actively cooling the device. Fortunately for us, with the sodium, those wavelengths are long enough, or sorry, the energies are high enough, the wavelengths are short enough that we can get away with an uncooled receiver system. Whereas once you move to like 1083 nanometers, where there could be a lot of background light, and then thermal noise, of course, in the receiver system, then we might have to think about cooling the device.
So, Peter, so far you've given us a fantastic description of the challenges involved in your specific research. I'm curious, what other types of LiDARs exist, and also if you can also talk a little bit about opportunities and where this field is going, that would be great.
Sure, that'd be wonderful. Thanks for the opportunity. So, other types of LiDARs. Well, we've already discussed the resonance fluorescence systems. Others are based on either the elastic or inelastic scattering of light from the atmosphere constituents. In the case of elastic scattering, these are based on scattering from molecules or aerosols. Usually we think about Rayleigh or Mie scattering in that case. For example, upper atmospheric, such as exo or mesospheric Rayleigh LiDARs are most often used to track dynamics in those regions of the atmosphere. For example, one such dynamic process involves gravity waves. These are distinct, of course, from gravitational waves. They relate to the motion of the atmosphere up and down vertically with time. Importantly, tracking events such as these things also helps us understand how energy couples between the regions of our atmosphere and enables global energy transport models. Aerosol LiDARs can, for example, be also used for tracking air quality near the ground, so pollution sensing and that kind of thing. LiDARs that make use of Rayleigh or Mie scattering also include something that LiDARs known as differential absorption LiDARs. There, what you do basically is you have your laser beam. Again, it's pulsed most oftentimes to do ranging, and then you tune your laser beams on an absorption feature and off an absorption feature. If you know what the absorption cross-section is for that feature, the ratio of those two signals gives you a relative abundance of that constituent. So these types of LiDARs can be used to measure greenhouse gases, again, such as water vapor, as I had worked on in the past, and carbon dioxide, for instance, as well. These two atmospheric constituents, among others, of course, can be measured in the near infrared. That means that we can use less expensive and possibly less noisy sensors and less expensive lasers, for instance. Other gas sensors, such as those that look for nitrogen or sulfur oxides, require lasers in the mid-infrared. which is more challenging from several perspectives. Efficient lasers at those wavelengths producing sufficient powers, especially if you want them to be pulsed. Detectors, of course, now you're talking about low bandgap materials. They become more noisy receivers. You also have Doppler systems that make use of Rayleigh scattering, but the receiver is able to measure a change in the frequency, right, or the Doppler shift. These systems are often, actually these days, commercially used to measure wind speed in the vicinity of wind turbines. Other LiDAR technologies based on inelastic scattering are like Raman and Brillouin lasers. Like Doppler LiDARs, these systems rely on the measurement of change of frequency of an outgoing laser signal, after interacting with the measurand. So for instance, we talked about Brillouin scattering. Brillouin scattering is an interaction between a light wave and an acoustic wave, oftentimes ultrasonic or hypersonic. The light scattered by Brillouin scattering, just like it is in optical fiber, is frequency shifted, and this frequency shift can be a very strong function of environmental things like temperature. So just kind of as a result of this, for example, Brillouin scattering-based LiDARs have found applications in ocean thermometry, which becomes a very important thing to measure. Again, global circulation models, not in the upper atmosphere, but in our oceans. LiDARs can also operate in both the time and frequency domain. We talked about pulse LiDARs, but the time domain systems, are pulsed. Again, these are time-of-flight systems. Frequency domain LiDARs, on the other hand, use frequency modulated continuous wave lasers, where the laser wavelength is swept in time. There, part of the output beam is taken as a reference or a local oscillator. And then, think about, like, you send a signal out, if our frequency is constantly scanning or sweeping, then the time delay between, what comes back and the local oscillator will give rise to a frequency offset between those two things. And then, of course, if we beat them together and measure the frequency shift, that gives us the time delay or equivalent of the distance. So lots of different ways to do this. As far as like opportunities and bottlenecks and things go, challenges. Again, there are a lot of challenges in the development of LiDARs. This is related to the laser wavelength and power. Going back to the automotive LiDAR application, eye safety becomes a concern, and this actually is a very significant, a very serious limitation to the ability of the feasibility of LiDAR systems. Again, we want a large telescope necessarily. We want high power, but you can't think about really putting power out that might damage someone's eye, and you also can't imagine putting 1 meter telescope on top of a car. So that's kind of one way to think about sort of a limitation. Again, low noise, high efficiency receivers can be a challenge, as we talked about. Silicon detectors have been developed for many years, very mature technology. The dynamic range available from them is also very large. We can do photon counting with silicon all the way up to high power measurements. But if the desired operating wavelength lies outside that spectral response of silicon, different materials have to be used. So again, some of these things aren't then amenable to photon counting, and so we have to think about different ways to detect these signals, such as a modern push towards things like far infrared, superconducting single photon receivers. So anyway, a lot of opportunities in new lasers, new receivers. For autonomous operation, of course, power, more efficient solutions are important. So we think about all those things as well. And again, as we talked about, the environment and the platform on which the laser is placed or the LiDAR is put is going to be a serious limitation.
Wonderful. Thank you, Pete, so much for spending the time going through lots of the details about not only your project, but also an overview of the opportunities and all the excitement around LiDAR technology. I have certainly learned a lot and enjoyed this conversation very much. Now I'd like to pass the baton to Akhil for the remainder of the podcast.
Thank you very much, Rajesh. Thank you very much, Peter. That was absolutely incredible. The amount of things that we've actually had a conversation about, and so much of what we can unpack through the course of the podcast and afterwards is incredible. And I thank you both very, very much for that. I've got a couple of questions before we close for today. And the first question, I'd like to keep Rajesh and Peter both interested. Now, obviously, as I have learned being a PhD student and an early career researcher and a postdoc, the first thing you do when you start talking to somebody is you Google them. and you find out what they actually do. Now, interestingly, with my background in biophotonics, everything that Peter does in terms of time of flight imaging, in terms of time of flight sensing, LiDAR systems, or low light conditions for LiDAR systems specifically, all the scattering methods, everything are also seen in Rajesh's research of brain imaging. Do you ever see the crossover across the fields? Do you think something in LiDAR systems would be interesting to Rajesh? And do you think something in biomedical optics would be interesting to Peter? A question to the both of you.
That's a very interesting question because although the different fields use different names, different words for technologies and methods, I mean a lot of the approaches are all identical. There FMCW, for instance, LiDARs, which you find on automotive LiDARs, automotive autonomous vehicle sorts of things. The same technology can be found in precision metrology, on the micro scale.
Mm-hmm.
So that could also include, bio applications and bioimaging things.
Because it's quite interesting when Peter was talking about everything he was mentioning. He was talking about fluorescence, about LiDAR, about Rayleigh scattering, all of which I'm sure Rajesh and myself have seen in tissue imaging. So Rajesh, you were about to say something.
Peter's exactly right. I think there's a significant amount of crosstalk, and it's one of the reasons I try to actually talk to folks outside my discipline is that you not only recognize areas that are common, but new ways of solving very similar problems. So in dealing with scattering, certainly in macro scale imaging, people have applied time of flight for imaging through scattering media. In the microscopy community, because the dimensions are so small that the time difference of the reflected pulses are way too small, at least as far as I'm aware of, I think it's quite challenging. But I wouldn't say never, but it is a little more challenging than doing it for much larger distances, I would say. But fields like adaptive optics clearly have been applied in both areas. I mean, biophotonics, adaptive optics is pretty standard nowadays, but it was adopted originally from astronomy and completely different fields.
Absolutely. So. I mean, there's a big difference literally between a mirror used in a telescope and a mirror used in a digital micromirror device, but we're still effectively using a mirror.
Right. Yeah.
Yep.
So
yep.
It really underscores I think it's an important point that you're raising. It underscores the importance of understanding the fundamentals of whatever it is that you're learning, because it's, as an engineer or scientist, it's much easier to translate your skills to very different fields. So I think it's an important point to convey to the young engineers and scientists who are listening to this.
Absolutely. My next question, again to the both of you, is as quickly as you can and as easily as you can, what are the two things, one for a academic sphere and one for a personal, or here's a good advice to be a good researcher kind of advice, would you give to somebody listening to this? Where should the next LiDAR systems engineer focus on? Also, what should every young researcher try to do right now?
I'd say as a new, I don't want to use the word young because you may not be young in mind, young in a field, person entering a field. I think it's really important to really talk to as many people as possible to understand the landscape and understand the challenges, often which are not necessarily obvious or even written down somewhere. So it's really useful to understand the culture and the challenges of a field as much as possible. And the way I think it's an effective way to understand is, of course, talk to your peers, talk to your mentors, talk to your competing labs if there are any, go to conferences. Really try to talk to as many people as possible even if they're not directly related to your field, you learn a lot. This mean my personal experience. So.
Yeah, I can actually follow up on that. I agree entirely with that remark. I mean, Rajesh, you did your undergrad at MIT. Do you have
My graduate work, but go ahead.
sorry, your graduate work. Well, yeah, we can start over. Rajesh, I fully agree with the comments that you made. Those are very important points. I fully support them. I guess you did your graduate degree at MIT. Do you have familiarity with Olin College's user-oriented collaborative design course?
Oh, unfortunately not. Sorry. Please go ahead.
Okay. Yeah, well, I actually had the privilege of teaching that as a transplant here at the U of I for a few semesters. It was taught within the art and design program, and Olin College actually teaches that as a very first semester freshman course to kind of help students understand how to go out and find problems. It's not so much finding a solution to a problem, but it's going out and understanding how to find where the problems exist. What's a problem? A problem is something that could make someone's life better. A problem could be something that helps us understand our environment better. Anywhere where you feel like you might be able to make a positive change for humanity. And unless you're able to understand how to go out and find those problems, it's hard to understand whether the solutions that you're generating have any value or have any meaning. And so I agree. I mean, the whole idea, that course that I was involved with, actually got the students up out of the classroom into the field, talking to people. Hey, what do you think is important? What could make your life better? From the perspective of like a LiDAR system, what is it that we need to understand to really get a grasp on the meaning of global warming, for instance? Do we have to measure carbon dioxide? Or is there an atmospheric model somewhere where there's a scientist who's not a laser person says, hey, if we had this information, this would be transformative. And so, the student then can go out, find that problem, and then seek targeted solutions to solving that problem.
I think that's a very interesting sort of perspective and interesting sort of advice as well, because somebody I look up to quite a lot, in addition to everything that you've mentioned, has also quite vocally said that sometimes the people that you actually work with are almost as valuable, if not more, than the actual problem that you're trying to solve. And such is the nature of academia, such is the nature of industry, such is the nature of everything that we do today, that the people that we work with add so much more value. So going back to Rajesh's advice of speaking to more people, building those connections, and combining that with Peter's idea of here's a problem I would really, really like to solve, makes up for such a perfect motivational statement, for instance, for anyone taking on a project, a research problem across any field, really. And I think if you'd actually seen me on video while we were having this conversation, listening to the both of you, I was simply going, yep, they've answered that. Yep, they've answered that. Yep, they've answered that. So you've left me with almost no questions to ask, which is really, really good. I'm going to end today by thanking you both for your time. It's been a wonderful conversation. We have heard about LiDAR systems, about how Martian atmospheres can be measured and monitored, the value of it for astronomy, looking at fluorescence, looking at low light problems. We touched a little bit on brain imaging, although that's tangentially related. However, as in research, everything is connected. I think one of the biggest takeaways for me was how multidisciplinary and interdisciplinary research today and problems today have become. There's electronics, there's optics, there's rocket science. And never before today have I realized how much someone like Peter would really like his laser back after it's gone to space and come back. So I think that's quite nice. A journey of a laser that's probably traveled more than me.
Yeah. I do have one last question for you, Akhil.
Yeah, absolutely. Go ahead.
Before we end, what are some key takeaways that we, as more advanced in the careers, should know how we can support early stage researchers like yourself and your peers?
Okay, so how much time do you have? I've got a list. So I think the conversations that people could have, there is a innate fear when it comes to every early career researcher and PhD student to walk up to an established academic at a conference and go, here's a question I have. I read a paper that you published, and I think I have a few questions. Would you have an opportunity for a conversation? I think as in most academics and I correct myself. Most early career researchers are looking for a mentor, somebody who can either be a mentor for a long duration, somebody who's at the other end of their career to turn and say, I will guide you throughout this procedure, or somebody who can answer a question as best as they can in that moment, effectively helping them along their journey. I think the best contributions I have had from established academics from their careers to mine was simply time. Just the opportunity to talk to somebody much further along in the journey, and for them to effectively tell me, I did this, don't do this, or I did this, I think you should also do this. I think there's no better support than a good mentor, some good advice, and a general supportive nature, really. So does that answer your question? I've got a bigger list though.
Excellent. No, that's a fantastic place. Yeah.